Hey everyone, in this video I'll show you how to download the Ltspice from Google, from Analog Devices website. So all I did was just type in Analog Devices Ltspice download. The very first link would be Ltspice Information Center. Click on it. There will be 3 links. Just scroll down for Windows, Mac, and this is what I have on my laptop. It says no updates available, but it doesn't matter. Ltspice is pretty good for simulating circuits, so you can download this or this, it doesn't matter. Once you download, it just gets downloaded in C folder, program files. Sometimes it also gets downloaded in program files. It says x86 and in LTC folder. So the LTC folder, if you click on it, it shows the Roman number for the Ltspice version. There are a couple of examples given, educational examples. You can take a look at it. Then there are like a library which has symbols, components and everything. All the ADCs, comparators, op amps. This is where the Ltspice gets downloaded. And when you open it, you will see this symbol. It's nothing but the author, the inventor of Ltspice. You can read about it. He just incorporated this specific tool. I think it has something to do with astronomy. You can read about it. It's basically, it's not some kind of error or compatibility error on Ltspice with related to Windows or Mac. It's just this symbol, he incorporated it. You can look at the toolbar. The very first thing I will do is click on File, New Schematic, or you see this symbol, it says New Schematic. I put my cursor over here. You can do File, New Schematic as well. It just comes over here. On here, if you just put your cursor, it would show you what it does. New schematic, folder, save. These are the tool options. The running man is after you design your schematic, you can run the schematic. This is just zooming. This is like zoom out. And this is like if you want to cancel one of the components when you place it on the schematic. And this is just to copy, search. This is a wire to connect 2 components. It's like, let's say I place the resistor on my Mac. Somehow it places 2 of them because of the click on the keypad. So you can just click on the resistor here, just place it over here and hit escape. I have to use scissor because, as I told, I'm using Ltspice on parallel software, which is a tool for running the Windows machine on Mac. And whenever I put the schematic component, it somehow places 2 of them based on the click. On Windows it should be okay for you. And this wire is nothing but it comes up like this. All you do is click on this specific spot of the resistor, and this specific spot, it just connects 2 of them in parallel. So this is the wire function. I can just select everything using this and just hit scissor. All I did was, or I can do this, I just selected the move command where I selected it, and you can hit escape if you don't want anything. This is the drag. This is the component placement where we'll place resistor, capacitors, voltage sources. It's a very simple. Ltspice is very simple to understand, and it's a very simple tool. This is the diode. If you want to place a diode over here, click on it and just place the diode and hit escape. Use the scissor just to cut it. This is the capacitor. This is the resistor. This is like a label net if you want to label a net. This is the ground. Before getting into the schematic, I would like to show you, go to tools, control panel, or let's go to color preferences. this just tells you the background color. If I don't want let's say the grid or the background, click on background. You just change this number, so it changes the color of your I don't want this gray type of background. You just change it, you just change the number. You don't like the wire, you can change the color of the wire. Just drag it like this, make it pink, white, whatever you want to do. I will keep it to default, which for me is okay. You can change the component body if you don't like it. You see it turns red over here, maybe yellow, maybe blue. You can do a lot of things. You can change the grid. You want the grid, you don't want the grid, make it 255 like that, and click apply. This is the and for the waveform as well, you can change the color, the background. I think the background is also over here. For the waveform, you want it white, you can change it. Then you have to change the trace. Trace needs to be 0. So I'll just take the default. I don't care about these colors. Click on OK. Then come over here to control panel. In control panel, we don't really need to get into the other things. This spice, when you click on the spice, this is what the Ltspice uses in the background. At the moment I have it in default. When you download it, it will be in default. You don't really need to change these unless you're having convergence issues, or there are some kind of spurious spikes on waveforms, or some kind of waveform that doesn't look like what it's supposed to look like, any kind of spurious spikes on the waveforms. Then what you do is you come over here under the default integration method. Especially you can change it to gear. That's one. The second is you can change the solver to alternate, which is quite accurate, fast. It's quite accurate. I shouldn't say it's fast. The maximum threads, I think it takes it based on your cores. I have 6 cores. The matrix compiler as well, I can change it to pseudo if I have some kind of convergence issues. I can change it to gear, alternate, pseudocode. Thread priority, it's up to you whether you want to put it high, low. On the right side you have Gmin, which is like a transconductance. I'll keep it default. It's transconductance. G is like 1 over resistance. Apps tall is like the accuracy of the current. Volt tall is the accuracy of the voltage. Rel tall is the accuracy of both voltage and current. Charge tall is the accuracy of the capacitive charge, the best accuracy of the charges. I'll just keep it default. If you want to make the simulation fast, you can change this number from 1 to 100. I'll just keep it to default. 1 will give you more precise, accurate simulation, whereas 100 would be fast but not really accurate. So I'll just keep it to default. And yeah, that's all you need to know over here. So just to recap, if you are having some kind of simulation runtime issues or convergence issues, then you can change it to gear, alternate pseudocode. Keep these default. I can change this number probably to, it doesn't make much of a difference, to 1e to the -10. Everything else I'll just keep it same. But for now I'll just reset it to default. I didn't really have any kind of convergence issues, but you can change these. The next one I wanted to show is if you come over here, you have resistor. I click on the resistor, just click over here. If you want to get rid of the R3, just hit escape. Since it's a Mac, it puts 2 of them. You can put your cursor over here, right click. You can change this to 10 ohms, and that's the basic resistance. You don't really have to do anything in resistance. Then you have inductance, which is this coil. Click over here. I'll just use scissor to cut one of them. This is the inductor. If you go to the inductor parasitics is something which is not visible to your eye, but you see an inductor. It has a parallel capacitor, which is like invisible, very small capacitance value, and it has a parallel resistance and a series resistance of the inductance. The wire itself has a resistance. So one thing in Ltspice is, if you want to make it faster, you can actually include the parasitic values. So what I did is, if I click on L, you can just put like 1 microhenry. This is the value. If you come over here and right click, you come over here on the symbol, right click, there is like peak current, series resistance. Ideally we want no resistance, but this is like an ideal one. You can make it like a 1 milli. So for 1 U, if you put a U, that is like a micro. If you put small m, that's like a milli. If you put capital M, that's like a mega. I think you have to specify like 1 mega ohm. If you say like this, then it takes it as resistance is 1 meg. 1 milli, 1 meg. So basically, the series resistance is basically the wire resistance, and the parallel resistance I was showing you. The parallel resistance, it's related to the core. What I mean by core is, an inductor is a coil wound on a ferrite material. So that ferrite material has some kind of core losses. When you pass DC current or some kind of ripple current is a current on top of the DC. It's like let's assume it's like a triangular waveform. A DC current, it's like a DC current. If this is the 0 and you have 1 amp over here, ripple current is something like this. It's usually this kind of waveform, you see it in power supplies. This is the ripple, the triangular waveform, and this flat line is the DC. So the parallel resistor is the core losses of the ferrite material on which the wire is wound. And the parallel resistance is the capacitance between the windings itself. When you wind it, there is an invisible capacitor between them. That's the parasitic capacitor. If you see the impedance of an inductor, it's like going up. This is like the Z versus the frequency. It goes up, then there is, at a very high frequencies, these parasitic invisible capacitances come into play and try to decrease the impedance. That's the basic inductor. So you can put 1 milli, you can put a parallel resistance of, let's say, 100k, or if you just want it very high value. Capacitance was like maybe 1 pico. If you put the parasitic elements with the inductor or the capacitor, when I'll show you how to put for capacitor, it makes the simulation faster. But I don't care, I'll just put 1 micro Henry. And if I want to build a transformer with 2 windings on a core, I'll click on the inductor again. I'll place it. Before placing, if you have placed it, it's okay. You can probably click on this one, it's a mirror, and this is a rotate. Or you can do Control R, which is for, let me click on Control R. I haven't placed the component yet. Click on Control R, it will rotate. Click again on Control R, it will rotate. You place it and hit escape. So now I'll probably make it maybe 2 microhenry. And you can put a coupling coefficient. How to put the coupling coefficient? You click on the Spice directive, or you hit alphabet S for Sam on your keyboard. It will come up as like this. I hit S and it opened up this Spice directive, or you can click over here, the very last button. And what you can do is you can put a K, which is the alphabet used for coupling between the two inductors. It's like two wires on a core, and you say L2, which is this inductor, space L3. I'll put 1. When you put 1, it's much faster simulation. If you put 0.99 or 0.98, the simulation I've seen will take little it will run little slow. And let's put 0.9 like this. So this is like the inductor and its coupling coefficient. If I want to show anything, like I can if I want to show the parasitic inductance, what I would do is I'll just click on, I will if you look at the previous screen, I had put like 1 milli, maybe a parallel resistance. Let me show you 100k parallel capacitor 1 pico. Okay, now it doesn't show, it only shows the inductance value. If I want to show it, the ESR, which is equivalent series resistance, and the parallel resistance, I hit control right click on this symbol, so it shows up like this. There is a visible. I hit control right click on the component and it shows up this component attribute editor. Click on visible and click OK. So now you can move this using the move command. I click on here, click on this, place it over here. That's it, and hit escape. And this is to zoom full extent, this one, or zoom out. So Ltspice is a very simple, you can just select and you zoom in. It's a very simple circuit simulator. It's free. You can do a lot of things. What else can I show in terms of the inductance? You can put another winding and you can still do L2, L3, L4 and have a coupling. You can also put L4 inductor, have that if you want to put another one. And turns ratio of inductor, if you know the basics, L primary over L secondary is N primary over N secondary whole square. So based on the turns ratio, you would know the turns ratio here. You can calculate the turns ratio, 1 divided by 2 N primary over N secondary whole square, and you get the turns ratio. Similarly, we can do it for capacitor as well. You can click on this component capacitor, you place it on here, hit escape. You can probably right click on this component, right click, 1 microfarad capacitor, 10 micro, it's up to you. It also has a series resistance, inductance. This is the parasitic model of a capacitor. It has a leakage resistance, it has the ESL, which is related to the copper, or the body, the wire that is connected to the body of the capacitance. It has an inductive component as well as the equivalent series resistive component. So this is the parasitic model. You can probably do the same for a capacitor as well. You can probably put a series resistance of maybe 1 milli. Ideally we want it to be 0. You can put an inductive 1 nano henry parallel, maybe very big 1 meg, or you can also do 1000k if you are not sure, small k. You can show it as well. So control, right click on here, you can make it visible, okay, as well. So I'll zoom out a little bit. That's with the capacitor. And you have diode over here as well. If you don't, you can put a diode and hit escape. When you right click on that, I just did a right click, pick a new diode, and you have a decent amount of selection, and they already have the diodes on semi. You can scroll down, they have a breakdown voltage of 200, 1 amp. You can just select it if you want. I'll show you how to install the model as well if it's not in the library. Then you also have, click on this AND gate symbol, which is a component, and there are a couple of things here. You can place an NPN transistor, place it over here, hit escape. You can right click by putting your cursor on this, pick a new transistor. You have several models here. You can also do NPN, PNP. You can do NMOS, which is a MOSFET as well, and everything has a model in here. Just in case you can't find a model, I'll show you how to put a model as well. So it has silicon, silicon X, Infineon, Alpha, Omega. A lot of models are there. If you click over here, it's like high to low or low to high. Right now it's at a ascending order, descending order. You click on here, it's like R on, the lowest one, highest one, like that. That's what diode, NPN transistor. What else can we show here? Like the voltage, I can show you the voltage source. Let's show. So over here you have voltage dependent sources, linear current dependent sources. You have behavioral model where you can use the BV as a, let me show first the voltage dependent voltage source. So you place it over here, hit escape. So it basically is going to, if I put 10, that means this symbol is going to multiply 10 times whatever the input is. It's like a behavioral model. And what else could you do? It's like a gain, voltage gain. And then you can also do, you can make it visible as well. Just I control right click, make it visible. You can also change it over here 10 times if you have some voltage of some specific node, like this. And there is a current source as well, voltage dependent current source. Just come over here. I think it's probably E or G. Yeah, voltage dependent current source. So the current is multiplied. I right click, or I can do 10 times v of node A or node X, whatever. So you can enter the gain to set a DC, to set DC to current gain equal to 10. So I just clicked on 10. That's the current gain. So basically the current will be 10 times whatever is at this node. So that's the voltage dependent current source, voltage dependent voltage source, and I wanted to show voltage. If you want to place a voltage, just type in voltage. You have this voltage over here, a DC voltage source, and you can put 10 volts here, any series resistance. That's much simple. Also over here, what you could do is, if you right click on this, if you right click on this component, you have advanced, where you can change to pulse, sine wave, exponential, PWL file. Right now it's a DC voltage source, so I have 10. Probably you can in AC amplitude value you can also place maybe 1 millivolt. This is for AC frequency sweep analysis. This will be needed. This is for the DC operating point. What else? We have a time domain, which is this sine wave. When you click on it, you can put an offset, something like this. So I have a 0. This is the offset voltage from here to here, and there is a sine wave with a peak value. That's what this really means. So I can put a DC offset of maybe 10 volts, peak amplitude of 20 volts, frequency is like a 60 hertz, time delay of 20 seconds or 10 seconds, 1 second. Theta is just the phase. Phi is the phase in degrees, and the n cycles. Theta is basically like the damping. I'll just keep it blank. I don't need it. I've never used it. The number of cycles you want to run 1000 cycles, you can do that. Phi is the phase in degrees, maybe 60 degrees, 90 degrees, it doesn't matter. You can click on this. So at that time you don't really need this one. You can do this. Let me move this one using move cursor. And amplitude, and this amplitude is basically the peak of the sine wave. You have a DC offset, you have peak of the sine wave. You can do it the same way for the current source as well. This is a time domain. When you click on the pulse, it's a time domain. Initial value is 0. Let's say it's 0. On is 20, delay is 60 seconds, rise time is maybe 1 nanoseconds. 1n means nano. 1 nano or 10 nano, or you can leave it blank. Actually, it's like a perfect pulsed voltage source. Period, you can have on time of 60 seconds, n of 1000 cycles. It repeats 1000 times. Basically, so cycles is 1000. This can be 100. On time is 60 seconds. The total period is 100 seconds. Basically, it means you have something going like this. So the on time is this part, the period is this part. This is one time period. From here to here is 100 seconds. From here to here on time is 60 seconds. 60 seconds, and the number of cycles, it repeats 1000 times. Yeah. What else? You can have a negative, you can start it from -10 as well. It's if you want, you can create your own waveform. And you have current source as well. Type in current, there's a current source, 10 amp maybe. A DC value, again it has the same advanced. You can do the same with the sine wave. Current as well, instead of voltage I was doing current, sorry, instead of current I was doing voltage. You can do the same DC value of 10 amps, or you can also use the AC amplitude of 1 milli, 10 milli, 20 milli. It's up to you for the AC analysis. It's exactly the same for current. Sine wave as well, it's the same. You can do the same pulse as well. What else? I'll just zoom out so that you can place a behavioral model, which is BV, arbitrary behavioral voltage source, which is like a comparator op amp. You can make it like a comparator, ideal op amp. So you can put an algebraic expression basically in this. If I right click on here, I'll just say V equal to maybe 1 plus it's probably an amplitude 3 times V of node A minus 2 times V of node B. You can write an expression here. It's like a op amp kind of thing. You can also make it like a comparator. You can put an if statement here. Right click, V equal to if V of node A is greater than 0, then make it a 5 volt or a 0 volt, like this. So you basically now replace this B1 with a comparator. So if node of A is greater than, let's say, 0, or let's say 10 volts or something, then make V of B1 equal to 5 volts, V of, or else it's 0 volt. It's the same for behavioral current as well. I would BI. It's all over here, behavioral current source as well. It's the same way. If I want right click over here and I would write the same type of current source, like I equal to maybe 1 amp plus 5 times the I of some resistance, let's say R1 minus I of R2. You can just change the amplitude. I want 100 plus 500 times I of R1, something like that. It's an algebraic expression you can put in. It basically replaces the op amp and comparator. If I of R1, or you can do this, I did right click, probably right click on this one, I equal to if statement, I of R1 is greater than maybe 1 or 2 amp, make it a 5 amp, or else it's a 0. That's all it's saying. So now it has replaced the comparator. So that's all I wanted to show in this specific video, just giving an overview of the behavioral voltage current sources, voltage dependent voltage source. Yeah, that's it. Thank you.